So let's quickly run through the quantum mechanics of the atom. So remember the Bohr model, which said that electrons go in fixed orbits around the nucleus, only works for atoms with one electron, in other words, hydrogen. Once you start to get to atoms that have more than one electron, then you see problems with the line spectra, such as shown above in this slide. So for example, if you look over at some of the blue lines, you can see that there's a couple of very closely spaced lines at each location, which we call the fine structure. And the Bohr model does not explain the existence of the fine structure, nor does it explain why some of those lines that you see are brighter than the others. Also, it doesn't explain chemical bonding, why some elements like to bond stronger than others, why there's some that have ionic bonding and some that have covalent bonding. And so we need to go to the quantum mechanical explanation of the atom, in which electrons act as both waves and as particles. So remember these problems with the Bohr model, these different ideas are things that might come up as concepts on a test. So you need to be able to explain why the Bohr model had to be replaced with the quantum mechanical model. Okay, so Schrödinger's equation is a wave function for matter. So when electrons or protons behave as waves, we can express their probability to be in a location x at a time t by taking the square of the wave function, which gives us the probability. So a diffraction pattern could be built up by electrons landing at each location. The areas where you see the red or the blue is where it's more likely to be, and where you see black is where it's less likely to be. So instead of orbits with a fixed radius, we're going to say that the electrons exist in a probability cloud around the nucleus, as shown in the picture at the bottom. So you can see that the dashed line is what Bohr's model would have predicted for the n=1 state, whereas that orangish cloud shows you the probability. The darker orange is more probable. So the higher the value of n, the more probable it is that the electron is further from the nucleus. So that dark orange region will move further away from the nucleus. So instead of just the one quantum number, n, we actually need 4 quantum numbers to describe the hydrogen atom or any other atoms properly. So here are the 4 numbers described in table form, and I'll walk you through each of them. So the principal quantum number, that's the one we had from Bohr's model. N was just an integer from 1 to infinity. And remember, the value of n gives you the energy, where En is minus 13.6 eV over n squared for hydrogen. And remember, the bigger the value of n, the bigger the radius of the orbital. The orbital quantum number L gives us the angular momentum. So these electrons are orbiting around the nucleus, so they have an angular momentum. And L can be an integer from 0 up to 1 less than n. So if n=4, L could be 0, 1, 2, and 3. The value of the angular momentum, capital L, is equal to root L plus 1 over h bar. And remember, h bar is Planck's constant divided by 2 pi. So it's just a constant. M sub L, the magnetic quantum number, tells you the projection of the orbital angular momentum. Remember, angular momentum is a vector. So in the picture at the side, you can see examples of 5 vectors that are all the same length, but they have different projections along the z-axis. And for quantum mechanics, the orbital angular momentum has quantized values for the z component, where it can be ml times h bar is the magnitude of the projection of each of those vectors on the z-axis. The integer ml can range between minus L and plus L. So that for this example here, where L is equal to 2, it can range from minus 2 to plus 2. So there's 5 different possible projections of the orbital angular momentum vector along the z-axis. And finally, we have the spin quantum number. Ms is either plus a half or minus 1/2. And so you can imagine that each electron, in addition to orbiting around the nucleus, is also spinning on its own axis, which gives it another angular momentum, which we call the spin. We have either spin up for ms, which we indicate by upwards arrow, and spin down, a downwards arrow for ms of minus a half. And these two spin values have very slightly different energies, and that explains the fine structure, the twofold splitting of the lines in the spectra. When chemists talk about the different orbitals, they talk about the L value in terms of a letter rather than a number. So S is for 0, P is for 1, D is for 2, F is for 3, and then we just go through the alphabet G, H, I, etc. for 4, 5, 6. And so spectroscopic notation is NL, where N is the number for N, and L is a letter. So if we're 4P, that tells you N equals 4 and L equals 1. So the angular momentum quantum numbers L and ML don't affect the energy levels very much. They do slightly, but they change the shape of the electron cloud. So you can see there's 3 different shaped clouds for N equals 2. When L equals 0, it's sort of spherical. When L equals 1, it can be either a dumbbell or sort of a donut shape. So what are typical concepts you should know? So you should understand the possible values you can have for each of these quantum numbers, and you should also be able to solve problems similar to this. So for example, here we say we have an electron that has an energy of minus 13.6 over 9 eV, and it has an angular momentum of root 6 times h bar. So what is the n value and what is the L value? So we say we've got 13.6 over 9, so that means that n squared, if I compare the equations, is equal to 9, so n equals 3. So my n value is 3, so it's got to either be C or D. All right, so what is my value for L? So P is L equals 1, D is L equals 2. So I know that L is equal to root 6 times h bar, so that means the thing under the square root, L plus 1, is equal to 6. So what 2 integers can I multiply to give me 6? Well, 2 times 3 equals 6. So that means L is equal to 2. All right, so it's going to be the 3D state. So you should be able to do sort of little deductions like that. All right, another question, the 3D energy level in hydrogen, how many different values of ml does it have? So we say, well, the D is the L. D is for L equals 2, and ml goes from minus L to plus L in integer steps. So it could be minus 2, minus 1, 0, plus 1, or plus 2. So that's 1, 2, 3, 4, 5 different values. And in fact, for each value of L, there are 2 times L plus 1 different values of ml. So here, for example, I've got L equals 2. 2 times 2 is 4, plus 1 is 5. So there's 5 possible values of ml. If I have L equals 1, I can have minus 1, 0, plus 1, which gives me 3 allowed values. So 2 times 1 is 2 plus 1. All right, if I have L equals 3, then I can have 2 times 3, which is 6 plus 1, or 7 different values of ml. Okay, so that explains the fine structure. Why are some of the spectral lines brighter than others? Well, it turns out that when an electron jumps up or down in energy, the only allowed transitions are those that have a change in an L value of either plus 1 or minus 1. So that's going to make some of the transitions more likely to occur than others, and thus those ones are going to be brighter because there's going to be more photons emitted with that color, that energy of light. So for example, here for lithium, the lithium, once I've got an electron up in the 3s state, which is an excited state, it's got higher energy than the ground state, it wants to jump down. So it could jump to the 2s or the 2p site. Which one is it going to jump to? Well, if it goes from 3s to 2s, its L value doesn't change. So delta L equals 0, and that's forbidden. If it goes to the 2p state, it's going from L equals 0 for S to L equals 1. So here delta L is plus 1, and so that one is allowed. So only the 2s to 2p transition is allowed. All right, so what happens if we have atoms other than hydrogen? So we've got multiple electrons. We have to put them in, got to assign them values of N, L, ML, etc. And so we're going to use the Pauli exclusion principle, which states that no two electrons can have the exact same set of quantum numbers. So if I've got two electrons with N, L, ML, and MS for each one, at least one of those numbers has to be different. You can't have two identical numbers. So how do we do it? Well, we put in the electrons in order of increasing energy. So it means fill N equals 1, and then N equals 2, and N equals 3. And the ground state of the atom is the lowest energy combination of all the electrons. So once you put all the electrons in to their lowest possible sites, obeying the Pauli exclusion principle, that is the ground state. So what's the rules? Well, first of all, we fill up the N equals 1 shell, then we fill N equals 2, and we move our way up. When we fill the subshells, which are given by the L value, we first fill the L equals 0, then we move up to L equals 1 if it's there, L equals 2, etc. Once we finish filling all the L's, then we move up to the next N. And again, remember, for our nomenclature, we're going to use the number for the N value, the letter for the L value, and we're going to put a superscript which tells us how many electrons there are. So for example, here we have 2p3, which tells us that we have 3 electrons in the N equals 2, L equals 1 state. So as I said before, each subshell has 2 L plus 1 possible values of ML, and for each value of ML, we can have either spin up or spin down, plus or minus 1/2 values for MS. So that means we have 2 times 2L plus 1 electrons that we can put into each of the subshells. So the S subshell, which has L equals 0, can hold 2, P can hold 6, D can hold 10, F can hold 14. When we're putting in for any given L value, we're going to put in all the spin ups first and then the spin down. So let's do some examples. Okay, so let's look at helium. Helium has 2 electrons in it. So we're going to start off with the N equals 1, L equals 0. So remember, for N equals 1, I can only have L equals 0. I can't have L equals 1 because L can only go up to 1 less than N. So L equals 0, the only allowed possible value for ML is going to be 0. So if I look at my N, L, ML, and MS, N is 1, L is 0, ML is 0, and I can have either plus 1/2 or minus 1/2. So once I've done that, I've used up my 2 electrons, so the ground state for helium is just going to be 1s2. So N equals 1, the L equals 0 state, and I'm going to put 2 electrons in. And again, note when I put them in, I put in a spin up with an upwards arrow and a spin down with a downwards arrow. Okay, what if I have a third electron? So I move on to lithium. So now that third electron, I've totally filled up the N equals 1 state. So now I've got to go to N equals 2. Right, so N equals 2 can have 2 possible values of L. It can either have L equals 0, which can hold 2 electrons, or L equals 1, the P shell, which can hold 6 electrons. So I have to start with the lowest value of L. So I'm going to put in my 1 extra electron in the L equals 0 state, and I'm going to put it in as a spin up, because the rule is we first put in all the ups and then we put in the downs. Let's move even further up. So let's go to sodium, which has Z equals 11. So I can put 2 in each S state. So I can put 2 in there, 2 in there. So I've got 1s2, 2s2. Now remember, L equals 0 means S. L equals 1 means P. You can see I have 1, 2, 3, 4, 5, 6, 2p6. So that gives me 10 electrons total. I got to put in one more electron, and now I've filled up my n equals 2 shell. I can't have any higher values of L. So now I have to go up to n equals 3. So I'm going to put in 3. The lowest value of L is S. And I've got one more electron left, so I'll put in that one electron into the 1 state. So my ground state for sodium is 1s2, 2s2, 2p6, 3s1, as is shown here. So the ground state configuration can be shown as an energy level diagram there on the right, or as the ground state configuration with the spectroscopic notation. So let's look at what happens if I go 2 more electrons. So I'm going to put in 2 more electrons. That's aluminum, Z equals 13. So we know we can put 2 in n equals 1, 8 in n equals 2, and then we're going to have to put the remaining 3 into n equals 3. So how do they go in? So first we fill the lowest n and the lowest L. So I can write down my chart, so I can make one column for L equals 0. L equals 0 has only ML equals 0. And I can show my L equals 1. My P states have 3 possible values of ML. So I make 3 blanks for ML equals -1, 0, and +1. You can put this in any order you want. I'm not going to be picky about that. And then we start to fill them up. So start off with the 1s, which is actually cut off on the bottom of the slide by my taskbar. So let me put that in there. There's my 1s. My 1s, I'm going to fill it in. I'm going to put a spin up and a spin down electron in there. And so those are n equals 1, L equals 0, ML equals 0, and MS is +0.5 and -0.5. Okay, then we do the 2s level. 2s has n equals 2 and L equals 0. The only possible values of ML are 0, and I can put in a spin up and a spin down. So there's the first 4 electrons. Now I'm going to move up in energy. Next one up is 2p. So for 2p, n equals 2, L equals 1. I put in my electrons. I put in all the ups first, then I put in the spin downs. Okay, so if I had less electrons, if I had 1 less, I would stop there. So 3 up and 2 down. All right, so I'm going to fill in that level, put in all my possible values. N equals 2, L equals 1, and then I put in all my spin ups for ML equals 1, 0, -1, and all my spin downs. Okay, next 2 electrons are going to go into the next energy level up, which is 3s. I can put in an up and a down. So 3s has n equals 3, L equals 0, ML has to be 0, and then I have spin up and spin down, so plus or minus 0.5. All right, so my next electron, only 1 left, has got to go into my next energy up, which is 3p. So n equals 3, L equals 1, and I put in 1 spin up electron. And the ML value you put in, again, I'm not going to be picky. You could put in whatever you want, -1, 0, or +1, but it's got to be MS of +0.5. Okay, so when I ask you to draw an energy level diagram, I prefer you to do the one that's shown on the lower left, which is the physics way of doing it. Chemists sometimes do it in the way that's shown on the top. And if this is the way you've been taught, I'll allow you to do this. So what chemists do is they draw little boxes. And so I'll draw lines between it. So each of those lines represents a subshell. So this is the 1s subshell, the 2s, the 2p. Remember, the 2p can have 3 different values of ml. So each of those boxes is for a different value of ml, and you can put a spin up or spin down electron into it. So you may also draw it as shown at the top. Once you get beyond 3p, the filling becomes a little bit more complicated because it turns out that the next energy level up from 3p is actually not 3d, but 4s, and then you get 3d, and then you get 4p. Okay, so actually I should have drawn 3d, should have been over here, 3d, and then you get 4p. So a way to remember which order to fill them once you get into the higher elements in the periodic table and the transition metals is to do these diagonal arrows. So first you fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. If you have more electrons, you do 4d, 5p, and you keep going through this as you get through the rare earth materials. All right, so let's just talk about understanding energy level diagrams. So based on this energy level diagrams is shown here in the blue, the orange, and the green. One of these is the ground state. One of these is an excited state. An excited state has higher energy than the ground state. And one of them is a forbidden state, so it's not allowed or impossible. All right, so which is the ground state? Well, the ground state has all the electrons in the lowest energy configuration. So which is the lowest energy configuration? Well, it looks like this one in the orange box is, but if you look in the orange box, I've got 3 electrons in the 2s state, but I'm only allowed to have 2, so this one is actually forbidden. So which is the next lowest energy? Well, the next lowest energy, remember, energy is increasing as I go up. So the one in blue is the next lowest energy, and then the one in green has the electron moved up from 2p to 3s, so it's higher energy. So the blue one is the ground state, and the green one is the excited state. How about if I give you 3 spectroscopic notations and I ask you the same thing? All right, so what do we know about the green box? So if I look at the green box, you can see I've got 1s is filled with 2, 2s is filled with 2, 2p is filled with 6, 3s is filled with 2, 3p has 8 in it. How many electrons am I allowed in a p state? Well, I'm only allowed to have 6. And here I've put an 8 electron. So this one is not allowed. That's forbidden. Okay. How about the one in the blue box? So let's see. I've got filled, 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 filled. 3p4. Remember, p state could have 6. But instead of filling my p state, I've put 1 electron up into the 4s state. So this one is an excited state. This electron really should be down here, and the ground state would be 3p5. So this one is excited, and the one in orange, so I've got full, 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 the 3p5 state. This is the ground state. So you should be able to look at spectroscopic notation or energy level diagrams like this and also be able to figure out which is a ground state, which is an excited state, and which is something that is not allowed. Okay, so the activity that I want you to do is to go through for vanadium, which has 23 electrons. You're going to need to use that chart filling table over here to fill it up properly. I want you to make an orbital diagram. So I want you to make a diagram like this for vanadium. I want you to write the spectroscopic notation, so in this form. And I also want you to make a list like I did of the NL, ML, and MS for each of the 23 electrons. So I want you to make a table like this that I did for aluminum. So you're going to have to extend it down. So obviously the first part will be the same as you put in the first 13 electrons, but you're going to need to add 10 more electrons. So you need to figure out what the different quantum numbers are for that.